Well, hello, good morning, and welcome to the final day of Zcon3. I'm Jack, or Strad, I answer to both, and in this presentation I hope to give you an appreciation for the kinds of things that we've done over the last, 2 years now, to achieve the performance that we required for the Orchard circuit that was deployed in the Zcash Network Upgrade 5. So to start off, what do we think of when we're thinking of performance in this context? The most easily recognizable things are like Provertime, which affects how long it takes for a wallet to create and send a transaction. Verifier time as well, but also proof size. And in a context like Zcash, it's the verifier time and proof size that matter the most. Because verifier time affects everyone who participates in the network who wants to validate the blockchain, versus prover time, which is localized to people who are creating transactions. And an individual can improve their hardware if they need to for proving, but that doesn't help everyone else verifying. So when we were looking at how to, the direction we're going to take in terms of optimizing Orchard, our primary focus was on verifier time and then proof size. The proof size mattering here because once we pin the circuit, we can't alter the proof size. Whereas we can make future improvements to proving and verifying time by introducing newer arithmetic for the underlying field math and stuff like that. But there are other things that matter in performance, like parameter size and generation time can matter if you're trying to generate your circuit parameters live, which is what we currently do, or if you're trying to store them. And then proof of memory usage can also matter for constrained environments. We didn't specifically optimize it for our circuit, but it is something that you may, for Halo 2, the prover at the moment, but it's something you may want to take into account. And actually, there was a really good talk on the first day by Michele on, I think it was called Gemini, that you should go watch for more about interesting proof of memory stuff. So a brief overview of what I mean by Orchard. If you don't have an understanding of Orchard, but you have an understanding of sapling, you're good to go. Because Orchard is basically sapling, except that our focus was to migrate it to recursion-friendly primitives. And what this effectively meant was changing the primitive that we used for the root of spend authority from the jub-jub curve to the pasta curves. Which are recursion amenable via the way that Halo will be able to do recursion. So we made a couple of other small changes, but most of them don't really matter for this talk. So it is just a payment protocol. You can spend notes and create new notes, and that's about it. That's all that matters for here. So I'm going to start with a very energetic crash course to Halo 2. There will not be a whole heap of math in this talk. There's a link on one of the slides to the Halo 2 book, where if you're more interested in the math underlying Halo 2, you'll be able to look there. So Halo 2, what is it, sort of at a broad level? Well, we have taken the PLONK-style arithmetization, first proposed in the PLONK paper, and we combine it via relatively standard zero-knowledge proof techniques, with an inner product argument that is amenable to the Halo recursive technique. That's it. It's a relatively straightforward extension of the ideas that were available at the time when we designed it. In terms of the concrete implementations, we have the Halo 2 proofs crate, which provides the core proving system and APIs. Halo 2 gadgets, which is, if you're familiar with circuits and gadgets, having small reusable components to use, that's where all that lives. And then coming soon is the recursive logic. So to start off with what we're going to do in terms of what matters in terms of performance, we're going to start with our old friend R1CS. The rank 1 constraint system is a very popular and relatively simple arithmetization, by which I mean how you can take the protocol that you're trying to write as a circuit and encode it in a way that you can make a proof about. So let's start with this simple constraint system, simple protocol that we want to prove. we can write them into R1CS form, which is of A times B minus C is equal to 0, where A, B, and C are linear combinations of the variables in your circuit. So we can see we can write both of our constraints in that way, and then if we have the entire set of equations, we can then turn that into a matrix representation, where we have this witness vector W that refers to the variables in our circuit, and we have these A, B, and C matrices that encode the coefficients of all of our constraints. So let's take those matrices and just shove them over to the side for a moment. We're then going to take the witness vector and transpose it, and then just copy paste all the way down. So what have we just done? Well, what we have produced is PLONK-style R1CS. So PLONK is characterized by a table of cells, at least in the way that I think about it. So in R1, if you try to represent R1CS as a PLONK circuit, you can imagine having a bunch of columns, one column per variable in your circuit, and then 3 fixed columns with like constants baked into the circuit for each of your variables. And so you can see that if we take this general constraint up the top, which is just the generalized R1CS constraint, and fill it in with the values in each row, we get back the constraints that were in our R1CS circuit. Now, this is not at all an efficient way to build a PLONK circuit. If we were to take our system and put it straight into PLONK, I am missing a slide. Okay. Well, we end up with something that is significantly more efficient. In that we can now represent our, so our columns, which we've now renamed to advice columns that store our variables, they are no longer constrained to having a single variable. You can have multiple variables in the same column. You can now also have, not shown on this slide, but multiple constraints. So instead of having all of those constraint coefficients moved into the fixed columns, we can now represent them directly in the constraints. This does mean, though, that where previously the R1CS constraint could just be applied to everything, every single row simultaneously, we now need to control where these particular constraints are enabled. And we do that with a selector column, the S0 in this slide. So we can just take our existing constraint and multiply it by either some 0 or 1 constant value, and that will then either allow the constraint to constrain that row or allow you to fill in whatever you want. Another thing that PLONK gives you in terms of flexibility is this concept of querying relative offsets of cells. So in R1CS style circuits, like as we saw before, you're querying everything in one relative position, and there isn't any way to interact across rows. Whereas in PLONK constraints, you can think of your constraints as two-dimensional, like Tetris pieces. And so you can have interactions between adjacent rows. You can also have, there was the slide. So you can also have global constraints amongst your cells. So you can say that at any 2 points in this table, I require those to be equal. And you do this by enabling those particular columns to be used in this equality argument. And finally, the other thing that you can use with PLONK that is this concept of a lookup argument, which lets you essentially build lookup tables into your circuit. These are set up in a way so that if you have a particular set of values, you can specify that certain cells in your advice columns must be present within a set of the rows of this particular table. We can do that with this lookup constraint that we have in the top right here. Although note that, again, because the lookup constraints apply to every single row as per how PLONK works, if we want to be able to only look up on some rows, we have to introduce a selector, and that requires also defining a default value to bind into the lookup argument when you're not actually binding a cell. So all up, you can see that PLONK gives you a bunch of extra flexibility over R1CS in terms of how you can build your circuit, and that all of the extra pieces it gives you significantly increases the optimization surface that you have to deal with. which dealing with that is most of the rest of the talk. But actually, everything that this lets you do lets you build really fun and interesting circuits, and it's been so much fun to work with. Cool, so now that we have our arithmetic circuit encoding the protocol, in this case, the Orchard protocol, what can we do with this? Well, we now want to turn this into a proof. This is the slide that is replacing a bunch of math. Go to that URL if you wish to see the math. But in short, like we can look over what is going through on this in this workflow by looking at how we represent this table in the proving system. So each of the columns in this table abstraction are actually represented by polynomials in the proving system. So we start by taking any cells that aren't filled in the table, and we fill them in with random values in the witness values. That's actually a thing we do in Halo 2 to ensure that your circuit isn't accidentally relying on some default value being set, which is not guaranteed to be there by the because the prover can put whatever it wants into the advice columns. And from that, we derive a series of polynomials such that when you evaluate them at a value corresponding to a particular row, you get back the value of that row in that column. So we're generating a system of polynomials that represents the table, but it is in a mechanism that we can then do our proof server. And so we then take each of our constraints and we essentially substitute those polynomials in, corresponding to the columns. You'll note in particular that for the constraints where we are querying a cell on the same row, we just use the polynomial as is. Whereas if we are querying at a relative offset, we multiply by this particular value omega. I'm not going to get into exactly what that means. It doesn't matter for this talk, but you can see that essentially by multiplying by this value, we change what row we're referring to. And that's all that matters for this. But the key takeaways from this are we can now start to look at what is actually going to affect our performance. If you have more rows, or you have a larger maximum degree, sorry, I forgot to mention, you can set whatever degree you want. You're not set to degree 2. But doing either of those increases proving time because we end up with larger FFTs under the hood. And you can see from the previous slide that the number of rows and the maximum degree become multiplicative because of that substitution. Similarly, if you add more columns, well, each column is a polynomial. We have to commit to those in the proof. So we end up making the proof sizes larger. And verifying also ends up taking longer. Proving takes longer by the same amount of time, but there's such a disparity you don't notice. With more constraints, verifying also takes longer, but it's not as noticeable as columns, I believe, because you're modifying the computations you do to the polynomials rather than change the number of polynomials you're dealing with. In any case, everything is kind of connected, and dealing with that is the second part of this talk. We'll start off with the simplest kind of optimizations we can do. These are just constraint optimizations. So if you're familiar with building R1CS circuits, this is exactly the same thing. Minor optimizations in terms of how you represent Boolean constraints or decompositions, using non-determinism to say constrain that a particular variable must not be 0 by witnessing an inverse, the existence of an inverse. All of those kinds of things are the only thing you can really do in an R1CS circuit. But for a PLONK-style circuit, it's just the lowest level of optimization. And at this point in time, the easy bit. I mean, it still takes a lot to do, but it's something we're familiar with. And in fact, in the case of Orchard, we possibly overcorrected in this direction and went very heavy on these while we were still developing the later APIs for what we were going to end up doing. But all of this mostly operates in, again, that sort of R1CS, single constraint, single interaction model. But as we saw before, Plonk gives you 2 dimensions you can play in. And so let's take as an example this simple constraint. We're going to take an input variable, we're going to multiply it by 3 other variables, which the prover is going to witness, and we want to grab the result in some way. So we can represent this by a single multiplication constraint, where we say, okay, we're going to take one variable and another variable, multiply them together, and put the result in some other cell. So in this example here, we're placing the output of this multiplication constraint into the cell labeled T0. Now what this form of constraint lets you do is tessellate them, because you can enable, because it's 2-dimensional, but you can enable things at row increments. You can imply the constraint on 3 sequential rows, and because of the shape of the constraint, the output aligns with one of the inputs on the next row. So you can get very dense packing of your constraints. This in fact becomes very useful when you're building things like hash functions, or like Plonk for Poseidon, for instance, or ECC, so elliptic curve scalar multiplication for double and add, where you have a lot of like really dense packing that you can do if you can identify the that sort of repetition within your circuit. Questions at the end. So the T's are just temporary variables. They're interstitials. So they aren't represented in your overall protocol, but they need to exist as like a holding the output of one value to then use as the input to the next. And in general, when you are like taking some constraint and splitting it into pieces, you're going to have these interstitials. So you can see at the end of this, we end up with a like a little area that we're constraining that only requires 2 advice columns. And the constraint we're using has a maximum degree of 3. But it does require these 7 advice cells, including the 2 temporary values, T0 and T1. The other way we could represent this is to just use a single constraint that does all 3 multiplications at once. So this means increasing the degree of your constraint to degree 5, and additionally means that we need more columns in this instance to put our values in. But we no longer have our temporary values. We are just doing everything in a single step. You could, again, also have done this with fewer columns, but you would then need to change the shape of this constraint, which would make it less amenable to tessellation, potentially. But this is the kind of like low-level manipulations that you can do to sort of pack your components of your protocol like as efficiently as you can. Additionally, another optimization we can do at this level is query optimization. So I mentioned that a constraint refers to certain cells at certain relative offsets. So if we look at these examples, I've just taken the 2 previous ones and combined them, we can see that the first constraint is querying at the current row and the next row. And then the second constraint is querying at the current row and the previous row. Now, in the big slide that I skimmed over, one of the things that the prover needs to do is evaluate a bunch of polynomials at various points, including a point that represents each of the query sets in your circuit. So we look at all of the columns, A0, A1, all the way through, and we look at how many times a particular relative offset appears uniquely. And we build those together, we combine them together, and we end up with, in this case, 9 query sets. Now, each of those evaluations means 32 bytes in the proof, so this directly contributes to proof size. But if you can identify certain constraints where you can adjust their contents, so in this case, we've adjusted on what row we enable the selector, now both constraints query current and next rows, and they don't query previous. Our number of query sets drops to 7, we save 64 bytes in the proof. And this can have a reasonably significant effect. In the case of the Orchard circuit, we had 192 constraints, and the table that I'm showing now is horizontally we have all of the 10 advice columns that we had in Orchard, and for each one, which relative offsets we used. And in this case, at this particular point, we were using previous, current, and next in every single column. And then the ones are just this particular constraint is using this particular query set. And down the bottom, you can see the total number of queries of each kind made across all of the constraints. So by looking at this, you can see, for example, in the very bottom left, the prev offset in column A0 was only used 4 times throughout the entire circuit. That provides a particular optimization target for, okay, let's go and have a look at the constraints that is being caused by and see if we can manipulate them to alter what they're doing. We can't necessarily remove all of the relative usages, but we can adjust where they are to make better use of the relative offsets that you are using, which is the sort of I would say the general takeaway from this. And indeed, we were able to remove 5 query sets from the Orchard circuit. Now, doing so required splitting up a number of our larger constraints into smaller pieces, which meant having more selectors. And more selectors means that you are you end up increasing the base size of the proof that everything shares, because it affects it in some interesting ways. But the more obvious change is that every individual action no longer has to include the evaluations for those 5 query sets. So overall, it is a noticeable saving. So now we can also then look at the degree bound of our constraints. So this is showing all of the constraints that we have in the Orchard circuit based on what degree they're using. So as I mentioned before, the degree is combines with the number of rows to give you like the bounds on the size of the polynomials that you're dealing with. In the specific case of how Halo 2 is implemented, we end up at hitting a power of 2 boundary at degree being a power of 2 plus 1. So the maximum degree we picked for the Orchard circuit was 9, which is just before we would have increased the size of our FFTs and slowed proving time by a factor of 2. And what you notice is that I think there were 4 constraints we used that had degree 9. If we had wanted to, we could have potentially cut that down and cut some of those into pieces and then use, say, degree 5 constraints for those. But doing so adds complexity at that particular level, because if we can just use these constraints natively, then they become easier to review because they are closer to the protocol that you're implementing. But conversely, if you were not actually using you don't tend to use the very high degree bound very much, and doubling the degree bound is equivalent in performance to the cost to doubling the number of rows. But when you double the number of rows, you're generally going to get hundreds, if not thousands, more cells to work with. So in general, I would say focus on trying to keep a reasonable degree bound that fits with the sort of protocol you're trying to do, and instead pay the cost in rows if you have the option of either. Cool. So a lot of this is really fun to do at the low level, but it is incredibly hard to do these kinds of optimizations at scale. And we really didn't want to try and require everyone, particularly general circuit developers shouldn't need to be required to do these kinds of optimizations to get performance. So what we wanted to enable was the users of the Halo 2 system to make decisions about how they, where they did their optimizations. And so we wanted to enable automated global optimizations while still allowing these kinds of low-level manual optimizations for targeted performance. And the way we do this is with the concept of regions. So this is the same set of constraints as before, but now I've just overlapped them. So they're now tessellated and they're connected together. So the output of the first multiplier is added to this accumulator variable, and then we apply the second multiplier to get a total of 4 multipliers. So what we do in the Halo 2 API is we define the concept of a region, which is the bounding box around the assigned cells in a certain, well, in a region. So in the API, you go like layouter.assign region, and then anything you assign within that is deemed as being part of this region. So then we can consider using that region in a wider circuit. So in this example, we're now using this 4 multiplications region, and then it's interspersed with some other operation. Now, this interspersion comes from just like representing your regular business logic and just directly running through it and applying it to the circuit. This is going to represent sort of, it's going to be closer to like the execution of your business logic, but it is really not optimal in terms of packing, in terms of how we use the circuit space available to us. And so this is where we bring in the concept of floor planning, where we want to have so we have a API guarantee, like a contract at the boundary of a region. The proving system promises that whenever you define anything inside a region, it will only ever move those around while preserving relative offsets. So you can think of it as just like moving that rectangle around in the circuit. And outside of that, the prover can do whatever it wants. The floor planner can do whatever it wants. This means that you cannot use relative offsets outside of a region because they're not guaranteed to overlap in the way you want them to. But in exchange, it means that the layouter can now move those regions around and alter how they fit into the circuit to free up significant amounts of space within your overall table. And there are a bunch of other things that are possible to do when you have this abstraction. That being said, if you don't want to use the automated layouter logic, like certain very, very large circuits that are building on Halo 2 at the moment, you can just define a single region and then do everything inside that region, and then you're just back to the just playing Tetris with your own constraints. You are more than welcome to do that. We would like to try and make the automated stuff useful for you, though. So if you are doing that, absolutely come talk to me, and we will see what we can do to make improvements here. So now now that we have the sort of like boundary separation between the low level and the high level, we can now start to think about how we can enable top level users and builders of a circuit to customize their circuit for the particular performance target they have, proof size or verifier size or proving time. So if you're familiar with circuit programming, you are very likely familiar with the concept of gadgets, where we have some small reusable component of circuit logic that can be shared across multiple instantiations of a circuit. So in Halo 2, we fill these gadgets with chips. And the idea here is that we split the gadget logic in such a way that you can then, as a circuit developer, you can take a gadget and then plug a chip into it that, it might be optimized for, for a small circuit area and proof size, but be slower in proving time. Or you might have something that takes a bunch more space, but gives you significantly better performance. Similar to how you might do a similar thing with a silicon chip. You might have power optimized chips or performance optimized chips. And so what we do to enable this is we define the concept of an instruction set. This concept is directly taken from like, AVX2 or SSE4 instruction sets that you get in CPUs. So we can define a Rust trait that encodes the boundary the set of instructions you need to implement your gadget. So in the example here, I have a Merkle instructions trait, which it provides a hash layer instruction. And this performs the step when checking the Merkle path of a commitment tree to take two nodes and hash them together and produce the next node for the next layer. You can see that this Merkle instructions trait itself requires other instructions. You can see it's bound on sincere instructions in this case. And it also requires the ability to do a conditional swap, which we need to be able to handle like left versus right correctness in a Merkle path when you're going up through a Merkle tree. And so we can define this instruction, and then the gadget, like in this case the Merkle path constraint gadget, is implemented just using these instructions. And meanwhile, you can then implement like whatever you want in terms of a chip logic that just, as long as it implements this instruction set, you can use it. And when that instruction is called, so we can see we pass this layouter in, which is the representative of the floor planner in this logic, and the chip can then use the layouter to generate regions. So it's not required that one instruction corresponds to one region. Chips can do whatever they want under the hood. They can have like their own optimization trade-offs within them, but they also enable the high-level circuit developers to also make these, it allows us to expose those optimization trade-offs to the top-level circuit developer. I will note that this is all a shared fiction. Like, there is nothing in the Halo 2 APIs that requires you to do this. I tried, it doesn't work. So you can entirely build Halo 2 circuits without dealing in gadgets and chips at all. However, if we believe hard enough, then they will have power. And it's my hope that that if we have this model, then for at least the common gadgets that are available, then people will be able to use this in fun and interesting ways that without needing to like get into the depths of it. Like you might be able to prototype a circuit by just like pulling a simple chip or whatever's available off there, and then later when you want to productionize it, you can go ahead and write a more efficient for your particular instance chip. Or you might want to, for example, take the same circuit and run it in two different scenarios. Say one where you need to focus on proving time and you allow for big proofs, and then maybe in a recursive iteration or something, you then want to run it the same logic but with a focus on proof size. Cool. And the other thing that this lets us do at an API level is, so now we've essentially given responsibility to the chip author, the developer who writes those chips. They are responsible for the optimizations of individual instructions. But the gadgets themselves can also be optimized. So for example, in Halo 2 gadgets, we have this Merkle path gadget, which, as I said before, it allows you to check that some leaf node exists in a Merkle tree, which we do that quite often in Zcash. And so you can instantiate it with a particular chip that is given a certain number of columns to work in. And so it will take some input and it will call the hash layer instruction 32 times because we have a depth 32 tree in Orchard. But there's no reason that those all have to go to the same chip. You can additionally pass in two chips. And in fact, this is precisely what we do in Orchard. A particular chip has to be given a certain, at the moment, it has to be given a certain range of the overall table that it can use. This is actually a limitation we're trying to lift, but for now, the horizontal configuration of a circuit, like the number of columns and things, has to be defined statically. And so in particular, we have to say that this chip is going to operate over columns A1 through AK. But if we have a bunch of extra columns already for some other reason in our circuit, we can just use them and define a chip that uses those pieces. And then the gadget can just distribute the calls to the hash layer instruction across the two chips. This effectively gives us a direct trade-off between rows and columns, but now at the region level, well, the instruction level, and that then the chips under the hood will assign regions to. So it lets us do this two-dimensional optimization at another abstraction above the underlying constraints. There are a bunch of other things that we've also built into Halo 2. I don't have time, I think, to go through every of them in detail, but one that I do want to cover is this this assigned type. So it's very common in when you're building these circuits to need to perform some kind of inversion. So if you need to represent a division in your circuit, you represent that as inverting and then multiplying the results together. Now, inversions in the fields like the integers modulo large prime that we use in our circuits, this can be quite expensive, and it would be nice if you could batch those. There are ways to batch the cost of an inversion, so you pay some extra multiplications, but you only pay a single inversion per batch. And so we have built this into the APIs so that when you are inside a region and you're going to go and assign a specific advice cell, if that, all we require in the interface for that is that you provide some value. This is also another type that I don't have time to get into. But you just have to give it some value for that cell, as long as the value can be, so we can obtain this assigned type, assigned field element from that value. And you get to define how it is. If you just have an assigned type already, you can just use that. It's fine, it'll just do a copy. And what this then lets you do, the assigned type, implements all the same mul and add and sub, all the regular operations as a field element does, as a wrapper around it. But additionally, when you call the invert function, it just stores the inversion as a rational inside this enum, a numerator and denominator. And it just caches that all the way through. And then when you eventually call evaluate on that assigned, it will then evaluate the inversion. Specifically, it implements the inv0 operation. So if the denominator at any point is 0, then the result of the evaluating the rational will be 0. And in fact, we make sure that we carefully propagate that, because there was a bug in the original implementation of this. But what this then lets you do is, when you're computing your witnesses, that your values that you're assigning to your circuit during your business logic, you can just work in these assigned values. You can do your inversions, write it however you would want, and throw it into the circuit API. And then at the end of doing synthesis, of collecting all the business logic and building all the, collecting all the assigned values, the prover under the hood can then batch invert them. So this is a relatively small API affordance that we had to do. But it actually gives noticeable improvements. In the case I'm giving here, this was actually the Sincere implementation, because the way that the Sincere hash function works, every 10 bits of input requires 2 inversions. And in the Orchard circuit, I think we have 200, 300, we have a sizable, it's even more than that, it's 500-ish bits of input. So you're looking at 100 inversions that we now turn into a single inversion from this little API affordance. So yeah, we very much like building these APIs in ways that are as usable as possible for people. And then the last thing I'm going to refer to is feedback mechanisms. These are absolutely crucial for building performance circuits, because it's very well to do what you think is working under the hood and crafting your careful pieces, Tetrising together. But if you don't have something that you can measure that has enough granularity that you can see what's going on, then you're not going to be able to do that feedback cycle that you need to be able to properly optimize. One of the most powerful things that we built for this was a circuit visualization mechanism, where we could visualize the table form of the cells and actually see what was going on in regions. Use it, so I could stare at the circuit under my electron microscope, aka Microsoft Paint. But there were also other tools that we built for just taking either like some ideas about the circuit, like how many columns we'd have, how many like relative offsets we'd use in each column, and so on, or a concrete circuit that we built, and digesting out a cost model. So to look at, say, here's the proof size that this will result in, and here are the things that are contributing to that proof size. So we could find additional targets for optimization. And then, for instance, there was also a developer gadget I wrote that allowed you to extract constraint data from the circuit, and that was what I used for the query optimization giant Excel spreadsheet that you saw earlier. So yeah, the human optimization pass is incredibly important, and you know, we want to enable it as much as possible. It also helps you catch silly bugs. So both of the, this is actually the circuit visualization tool I was referring to, and we have the advice columns on the left, we have the fixed columns on the right, and the darker cells are the cells that are actually being assigned values in the circuit. You will notice there are the same number of assigned values in the circuit in both cases, and both of these were perfectly valid Poseidon chips, but I had a typo in my offset logic, and so I was introducing a bunch of empty rows inside my regions, which would have gone completely undetected and just made the Poseidon chip twice as large for no apparent benefit. So, yes, inspect your circuit layouts. So, all of the stuff that I've talked about thus far is sort of like the API affordances and things that we can do. But I want to cover just at the end a couple of concrete things that we actually did for performance. So this is another view of the circuit. This is in fact a view of the orchard circuit. On the left, you can see it roughly in business logic order, although if you look at the top left of the simple view, you can see that there are a bunch of there's like one big block of rectangles, and there's another one that's slightly further down. That's those are the Merkle tree hash layers that I described. So we can already see that even in the simple form, because all the simple layout it does is just take the business logic and go squish. It just slides everything up until it hits something else somewhere to try and fit it better. But when we then use the fact that all of these regions are connected by these equality constraints, so we can move them around arbitrarily, we then use a greedy first fit packing algorithm to figure out how best to shape these. And you can see we end up collecting a significant amount of space in the rows at the bottom of the circuit. Guess whose talk the other day is going to be trying to fit into that area of the circuit? I leave it as an exercise to the reader. Another kind of optimization that we built in, which again falls under the thing of floor planning, is a selector-combining optimization. So we described all those selectors that we use to turn on and off constraints in different rows. Well, what we can do is look at what rows, like once we've done the assignments during witness generation, we can look at what rows those those constraints are assigned on and combine them by sort of like selecting out columns that don't overlap, selectors that don't overlap, and using a representative constraint for that selector. So, for example, when you look at this compressed selector column C0, we can see that we can recover. We use we use an equation to represent the original selectors, so that, for example, if you look at S0 here, when you plug in 1, then the value becomes 6 because of the way the equation's set up. But if you plug in any of the other values, 2 or 3, it becomes 0. So we're effectively turning our selectors in this case from being Boolean, 0 or 1, into 0 or non-zero. Now, it doesn't actually matter, though, that they are 6 or -1 or whatever, because these selectors are only applied as a multiplication, constraining the entire constraint. And if you have something that needs to be 0 and you multiply it by any number, it still is required to be 0. So so we can use that to then basically, like, I think we end up compressing from I think we have something like 40 or 50 selectors down to around about 15 or so. And this is also why, when we did the query optimizations, we only gained 64 bytes because we added like 7 or 8 more selectors, but they combined down to only cause 2 compressed selectors to be added to the circuit. So this is the kind of horizontal optimizations that we can currently do sort of hard-coded in, but that we will eventually want to fold more things like this into the layouter. And finally, I wanted to make a very brief, because I'm starting to run out of time, comment on like the actual prover once we have the circuit. So let's say we have this particular constraint here. We can represent that as a diagram similar to like wire diagrams you might have seen in previous in earlier circuit representations, or an AST if you're familiar with those abstract syntax tree. So we can think of taking like our A0 cells, and remember those become polynomials that we substitute in, and we combine them via a multiplication operation. We then scale it by 4, and then we take that and we take another polynomial and we subtract them. So you can see that this is just one constraint, but in the process of actually building the polynomial, building the proof, we end up with one giant one of these operators that contains all of our constraints. In the case of Orchard, it's 192 of them, combined in various ways, and so on. And then some other things that enable you to do the lookups and equality constraints. So when we first implemented this, we implemented parallelization at the polynomial level. So if you took 2 polynomials and you multiply them together, a neat thing you can do is you can just take that polynomial, like all of its constraints, you can break it up into sections and then apply the multiplication to each of the individual sections across different cores, and then combine them back together. This turned out to be horribly inefficient because it was such a low-level operation that stripping it out at the end, and just going to single-threaded, gained us 15% performance, because we had such high switching cost for going into multi-threading. So what we ended up doing instead was we built this evaluator system that builds up this tree of operations as you construct them. And we also remember the polynomials that are involved at the leaves of this tree. And then when we come to the time of having to evaluate it, we break up the polynomials at the very beginning, shard them to each of the cores that we're using. We give each core a copy of the entire tree, operate over the entire tree in one go, and then combine at the very end. And that gave us something like a 1.82x performance improvement, again, over single-threaded. And there's more that you could do with this. For example, doing a pass to identify common subtrees within the tree and reusing those kinds of improvements. And that's the sort of thing I mean by we can make more improvements to Orchard proving time just through changes of this form that don't affect the correctness of the circuit. So what does this actually give us? I've just done some very quick benchmarks on my laptop, and if you look at a sapling circuit, Orchard has an action which is 1 input, 1 output. So for comparison, I'm doing a 2 input, 2 output sapling, and you end up on my M1 with a proving time for sapling of around 2.5 seconds, because it's about 1.2-ish seconds per spend proof, and you have 2 of those. And then it's about 1/10 of that, I think, for output proofs. So you end up with about 2.5. And verifying time, well, this would be roughly about the time to do batched verification of all 4 of the sapling proofs, because on order it's about, I think it's like something like 4 or 5 milliseconds, and then it's like 1 millisecond extra for each additional Grot16 proof you're verifying. And we end up with a total proof size of 4 Grot16 proofs of 768 bytes. And if we compare that to Orchard, we now have a proving time for a 2 action of 1.5 seconds, so we are faster than sapling, and a verifying time that is really within cooey of what we had for sapling. From memory, the way it scales is, I think for Orchard, the base time for a 1 action is around about 13 milliseconds, and it's an extra or 13.5, and I think it's then 1.8 or 2 milliseconds extra for each additional action. So it actually scales pretty well. It's always going to be slower than Grot16 because nothing is going to be faster than Grot16. But we've gotten pretty close, and that was our aim with this. There are obviously the cost here is in the proof size, but that was a cost we were willing to pay because we were wanting to move to a proving system that didn't rely on a trusted setup for, with parameters that we had to generate carefully. And the other thing that does, as a nice sort of aside, is that now that we don't depend on a trusted setup, it becomes very easy to change the circuit. All you're doing is you alter the parameters, you recompile, you're done. So this makes introducing later features like ZSAs or any other change to the circuit significantly easier to consider compared to what we had to do for Sprout and Sapling, which was make sure we got the circuit exactly right and then run a months-long process to securely generate the parameters for them. So this should increase the, not only increase the performance of building the circuits, but increase the performance of changing the circuits later, which is another nice benefit. So yeah, final sort of takeaways on this. Like I said, pick a reasonable max degree early on and sort of try and work within it if you can. Just look over your protocol and see what you're doing, what operations you're doing. Think about the internal repetitions within your protocol, both at the low-level operations within your primitives, and as well at the high level of your overall protocol that you can tessellate with regions. Visualize your circuit early and often and iterate there. And also join the new Discord. We've set up a Discord server specifically for the Halo 2 ecosystem. It's available at that URL. Also, if you want to get it afterwards, I'll tweet it out, I think. And I'll also put it into the existing Halo 2 channel on the Zcash R&D Discord, which is one channel is, I think, a little too small for this ecosystem now. So yeah, we'll have some more fun there. And with that, I'm ready to take questions. No, Kamrada first.
Yeah, so there are 5 questions on Discord so far. The first one is, how complex are the interactions between number of columns, number of rows, degree of constraints, etc., in determining proof time, proof size, and verifier time for Halo 2?
Somewhat complex. So the interactions, put it this way, it was quite easy to build the cost model. Well, it wasn't easy per se. It was possible to build the cost model for proof size. That was just a case of literally just going through the prove and verify protocols and just counting every time we did something with the proof and figuring out where it came from. Proof time is a trickier one to figure out, particularly while we were building the protocol. I've been meaning to go back and actually fill out that part of the cost model. The broad strokes I gave at the end of the first part are, approximately right in terms of essentially that would be my general answer to it. But in the specifics of building an actual circuit, you generally have to actually try and build the circuit, run through the dev tools and see what you get, and then iterate in that way.
There's a follow-up question. Are there highly nonlinear relations?
No, I don't think so. The only ones that you would introduce yourself, I guess. No, there's nothing specifically nonlinear in the proving system itself.
The next question is, in the big matrix of query sets, some of the columns appeared to be all 0. Is that because there are some constraints not shown on the slide?
Correct. I forgot to mention that. There are only about 27 rows that I could fit on the slide, and there are 192 constraints, so yes.
Would the chip abstraction generalize to multiple layers, like chips within chips, and would this be appealing for optimization purposes?
As I said, the chip abstraction is a shared fiction, so if you wish to define a chip within chip abstraction, you are more than welcome to. I'm not sure how I would convey that to users. The chip abstraction is already hard, given that it isn't concretely part of the API, but absolutely go ahead and try it.
How does sapling Groth16 batch verification compare with Orchard Halo 2 batch verification?
So we actually made some did some work on that for Zcash quite recently, and so the way that sapling batch verification is done, like I said, you're looking effectively just like, you have one base cost of one proof, and then you accumulate like it's about a millisecond for each additional proof that you're verifying. But they're quite, because for a Groth16 proof, you just have to take your instance variables and then just like a very short 3 polynomial proof, 3 pairing check proofs. There's not too much you can do under the hood, although there's stuff that we were able to do in terms of like combining the logic before to share the final exponentiation and so on. What we ended up doing for Orchard batching, it ended up being like the way that the Halo 2 proof is structured. We have all the verifier has to build up this vanishing argument constraint and like make sure it's built up the correct polynomial for that it expects, and so that sort of stuff. Like it ended up being easy to just do that single-threaded across a bunch of different cores. And then once you're done with that, you end up with this giant multiscalar multiplication you need to do. And for batching, that was the piece that we found easier to batch. We took the individual multiscale multiplications that we needed for each proof, and we concatenated them in the correct randomized way. And that was then the thing that we used batch logic on.
And there's a follow-up question. When does Halo 2 proof aggregation overcome proof size for Groth16?
It's never going to do so, I believe. So to clarify, the way that we implemented Halo 2, we built in private aggregation. So what we mean by this is you create a single proof for multiple instances of your circuit. In the case of Orchard, what this means is that we pay a base cost of about 2.7 kilobytes for using an Orchard proof at all, and then for each action, we add about 2.2 kilobytes. This is, just from those numbers, this is always going to scale worse than Groth16 because a Groth16 proof is 192 bytes. If you have 2 of them, it's 2 times that. And just concretely, that number it's the same kind of linear scaling, but the constant factor on that linear scaling means that the number of proofs for sapling is always going to be smaller than that for Orchard. But of course, the thing that we know that we can do with Orchard later is stuff like public aggregation, where you take existing public proofs and use nested or recursive techniques to combine them into a single proof over multiple existing public proofs. So it's not implemented in Orchard currently, or in Halo 2 currently, but that's the direction we see happening, and that is the sort of thing that will then help us to bring that scaling factor down. Okay, well, if there are no further questions, I will thank you for attending and enjoy the rest of the conference.